Happy morning, students. I welcome you all to the physics online class. How are you all? I hope you are safe and good in your home. Are you learning anything? Yes? Okay, last class what did you learn? Yes. Which chapter? 5th chapter, isn't it? What's the name? Acoustics. Have you remember? Yes. Under this, what and all we learned? It's a branch of physics, deals with the study of sound, isn't it? Yes, we learned about the sound waves, and the sound waves are longitudinal waves, isn't it? And based on the frequency, we have to divide the sound waves, categories of sound waves into 3 types: audible waves, infrasonic waves and ultrasonic waves. And also we learned the difference between the sound and the light waves. Okay, and today we are going to learn the velocity of sound waves. Okay, velocity of sound waves and what are the factors will affect the velocity of sound, and also reflection of sound. Okay, already we learned the reflection of light waves, isn't it? And today we are going to learn the reflection of sound and laws of reflection and the reflection at the different medium. Okay, the boundary of denser medium and at the boundary of rarer medium, and the reflection of sound in the plane and curved surfaces. Okay, have you all ready to listen the class? Okay, good. Velocity of sound waves. There are 2 types of velocities are there. Okay, you all know that what do you mean by velocity? Velocity means distance travelled by time taken. Okay, so here in the sound waves there is 2 types of velocity: particle velocity and wave velocity. What are the 2 types of velocities are there? Particle velocity and wave velocity. Okay, so particle velocity means what? Means the particles of the medium, in order to transfer the energy in the form of wave. Okay, particles of the medium vibrate in order to transfer the energy in the form of wave. That is called as the particle velocity. See, particle velocity means the velocity in the medium, there is a number of particles are there. You all know that. Okay, through that particles only the sound will be traveling. Okay, so the particle, when it is getting the energy, it will starts to vibration, isn't it? So that vibration is how much speed that vibration is there. Okay, the particle, how much speed it will be vibrating. Okay, so that is called as the particle velocity. Okay, so particle velocity, the particles of the medium vibrate in order to transfer the energy. Okay, particles of the medium vibrate in order to transfer the energy in the form of wave. Okay, before going to the waveform, how much the vibration is there in the particle. Okay, that is called as the particle velocity. The second one is wave velocity. So the velocity with which the waves travels through the medium is called as the wave velocity. Listen, the velocity with which the wave travels through the medium. Okay, after vibration it will starts to, in the energy it is in the form of wave. Okay, so that wave velocity, okay, after that how much speed the wave velocity is there. Okay, that is the wave velocity. The velocity with which the wave travels through the medium is called as the wave velocity. That is how much speed the wave will be traveling in the medium. Okay, how much velocity the traveling in the medium. Okay, that is the wave velocity. Okay, the velocity of the wave, how to calculate the velocity of the wave? That is the same formula. Already we know velocity is equal to what? Distance by time taken. Okay, so here the distance, what do you mean by this distance? Distance travelled by the wave divided by time taken. Okay, distance travelled by the wave divided by time taken. So how will you calculate the distance travelled by a wave? The distance travelled by one wave. Okay, that is the distance travelled by one wave. Okay, so in the medium, the how much the sound wave is travelled, isn't it? So this is one wave, one complete wave. Okay, the distance traveled by the wave. So this distance we calculated the wavelength. Okay, that is lambda. It can be represented by lambda. Okay, distance traveled by one wave. Okay, so distance traveled by one wave, it is equal to one wavelength. Okay, one wavelength, it can be represented what? Lambda. Okay, it can be represented lambda. Okay, so instead of distance we are going to substitute lambda. Okay, and time taken. So okay, time taken means capital T denotes the time taken by the wave. Okay, so one particular time how much wave is traveled. Okay, how much distance the wave will be traveling. Okay, that if you are calculating, we can get the velocity of the sound wave. Okay, let T be the time taken for this propagation of sound waves. So velocity is equal to distance by time. So here distance is equal to what? The distance traveled by one wavelength, that is lambda. Okay, distance traveled by a wave, that is wavelength. Wavelength can be represented lambda, isn't it? So V is equal to lambda by T. So distance, instead of distance we are substituting lambda divided by time. Okay, next we are introducing the next characteristics of the wave, that is the frequency. Okay, so frequency means, what do you mean by frequency? The intensity of these waves can be calculated by the frequency, isn't it? We already categorized the sound waves into three types based on the frequency. Audible waves in the last class we learned. Okay, here frequency can be represented by the symbol N. So frequency is equal to the reciprocal of time period. Frequency means what? The reciprocal of time period. So now we are going to, instead of this 1 by T, we are going to substitute what? The frequency. Okay, so here this 1 by T, instead of this 1 by T, what we have to substitute? Frequency. Okay, so V is equal, that is velocity is equal to N into lambda. N denotes what? This 1 by T, the reciprocal of time period. Okay, so 1 by T, instead of we are substituting N into this lambda. Okay, so the velocity is equal to what? Frequency into wavelength. Okay, velocity means what? The frequency of the wave into wavelength. Okay, so this is the formula for the velocity of the sound wave. What's that? Velocity is equal to frequency into wavelength. N denotes the frequency and lambda denotes the wavelength. Okay, now this, what about the velocity of sound in the different medium? Okay, the velocity of sound is maximum in solids. Okay, you know three types of matter: solid, liquid and gases. Under that, the velocity of sound is maximum in solids. Okay, do you know why? Why the velocity of sound is maximum in solids? Because the solid particles are more elastic in nature. Okay, comparing to water and gases. Okay, more elastic in nature. More elastic in nature in the sense, what is that? Atoms and molecules are here tightly bounded to each other, isn't it? So they are elastic in nature. Okay, that is the reason the velocity of sound is maximum in solids. Okay, and the velocity of sound is least in gases. Okay, the velocity of sound is least or very low in gas. Why? Do you know why? The gases are less elastic in nature. Okay, the atoms and molecules are loosely packed, isn't it? You all know that, isn't it? Okay, so the velocity of sound wave is least in gases. What is the reason? Gases are least elastic in nature. Okay, so in this three medium, how we can write the velocity of this sound waves? Yes, it is maximum in solids. After that only liquids, then last only gases. Okay, so the velocity of the solid is greater than liquid and it is greater in gases. Okay, so it is the velocity of sound is maximum in solid substances. Okay, velocity of sound is maximum in solid. Okay, after that only liquid, it will be faster. The last only it is gases. Okay, next we are going to learn what are the factors will affect the velocity. Okay, that is the velocity of the sound waves in gases. Okay, in the gas medium, what are the factors will affect the velocity of the sound waves in gas? Okay, see the factors. What are the factors will affect the velocity? Means the first factor is density. Okay, the density of this medium will affect the velocity of the sound. Okay, density of this medium will affect the velocity, and also the temperature. Okay, so the temperature also will affect the velocity. And the last one is the humidity of this air also will affect the velocity. So first we can see one by one. First factor will affect the velocity is density. Okay. See, the velocity of sound in gas is inversely proportional to the square root of the density. What is that meaning? If the density is more, means the velocity of the sound will be less. Okay. So based on the density of this particle, it will affect the speed of this sound. Okay, so velocity of the sound in gas is inversely proportional to the square root of the density. Okay, so here is the equation. The velocity is directly proportional to square root of inversely proportional to the square root of density. Inversely means 1 divided by d, isn't it? So square root of density. Velocity is inversely proportional to what? Density. So velocity decreases with increasing density. Velocity decreases with increasing density. So in the medium, the gas is medium. The density of this gas is more, means it will affect the velocity of the sound. Okay. So density increases, the velocity of the sound will decreases. So it will be travel slowly. Okay. The speed of the sound waves is travel slowly when the density of this medium is increases. Okay, so the first factor will affect the velocity is density. Okay, have you all understand, ma? Okay, then second one, the effect of temperature. The second factor will affect the velocity will be temperature. Okay, based on the temperature of the medium, it will affect the velocity of sound. Okay, so here just opposite density, that is velocity of sound in gas is directly proportional to what? Square root of temperature. What's that meaning? Yes, temperature increases means the velocity of sound also will be increases. Okay, in the gaseous medium, if you are increasing the temperature of the gas, the speed of sound will be travel faster. Okay, velocity increases with increasing temperature. Velocity increases with increasing temperature. Okay, so velocity of the sound in gas is directly proportional to the square root of temperature. Directly proportional means what's the meaning? Yes, increases, one term will increase, next also will increase. The velocity of sound increases with increasing temperature. Okay, so here the velocity is directly proportional to square root of temperature. Velocity is directly proportional to what? Square root of temperature. Okay, here one equation is there. That is the velocity at a temperature T is given by, okay, at a given temperature, how will you calculate the velocity? Okay, if T be the temperature, how we can calculate the velocity of sound? Okay, so velocity at the particular temperature, that is Vt is equal to V0 plus 0.61 T meter second per minus 1. You all know that this is the unit of this velocity. Okay, at 0 degree Celsius, let us take V0 be the velocity of sound. The gas at 0 degree Celsius. At 0 degree Celsius, what is the velocity? That one we have to take. Along with that, we have to add this 0.61 into that particular temperature. Okay. So, the velocity of this sound wave at 0 degree Celsius, that is the constant value. What is that? 331 meter second per minus 1. At a 0 degree Celsius, how much speed it will be traveling? 331 meter second per minus 1. The velocity of sound waves is changes by how much time it will change? 0.61 meter per second. What is this meaning? Per second, the velocity of the sound increases 0.61 meter. Okay. For a particular, that is 1 second, the velocity of the sound, how much it will travel? 0.61. So this much time it will be changed. The velocity of sound changes by 0.61 meter second per minus 1. Okay. For increasing each and every degree Celsius of temperature, how much velocity will be increases? 0.61 meter per second. Okay. I will understand. Yes. Temperature changes by 1 degree Celsius. Okay. For increasing 1 degree Celsius, how much velocity will increase? 0.61 meter. Okay. Per second. Okay. So, we have to add this value along with that equation. So velocity at particular temperature is equal to V0. V0 means what? Velocity of sound at 0 degrees Celsius. What's that value? 331. Suppose you have to substitute this value 331 plus 0.61. So what temperature we are going to calculate? That we have to check the temperature 20 degree or 35 degree. Okay, how to multiply. Okay, so we can get the temperature or the velocity at the particular temperature. Okay. Then third factor will affect the velocity is relative humidity. You all know that. What is humidity? Yes, that air pressure in this in the surrounding molecules, how much the humidity of this air, okay, the pressure of this air will be increases, okay, that is the humidity. When the humidity increases means we'll say that is today there will be the rain, okay. Now the humidity of this air, sometime we will feel more heat, isn't it? So that time what they will say, today maybe there is a possibility of rain, okay, like that they will say. So the humidity of this air will affect the speed of sound, okay. So humidity increases means the speed of sound will be increases. Humidity increases means speed of sound will be increases, okay. So this is the reason why you can hear the sound from the long distances clearly during rainy season, okay. So usually rainy season humidity of this air will be increases more, okay, comparing to normal day, okay. Rainy season time the humidity of this air will be increases. At that time the sound will be travel faster, okay. So that only we can hear the sound from long distances clearly during the rainy season, okay. So the humidity of the air will be affect the speed of sound, okay. Humidity increases means speed of sound will be increases. So these are the three factors will affect the speed of sound in gases, okay. In the gas medium, what are the three factors we learned? Have you remember? Yes, first one is density, the second one is temperature, and the third one is relative humidity, okay. See, in solids, what are the factors will affect the velocity of the sound is based on the elastic property, okay, that is density of this solids, okay. So the density of the solid will affect the velocity of the sound in solid, okay. And speed of the sound is directly proportional to the square root of the elastic modulus and inversely proportional to the square root of the density. Speed of sound is directly proportional to the square root of the elastic modulus, okay. That is elastic nature, what we studied. Yes, elastic modulus only, that is the atoms and molecules are closely packed in the what medium? In the solid medium, okay. And inversely proportional to the square root of this density, okay. So here the velocity of sound in solid is decreases as the density is increases, okay. When the density of this particle is more, so that only the velocity of the sound in solid will be increases, okay. Density increases means the velocity of the sound will be decreases, okay. And the velocity of the sound is increases when the elasticity of this material is increases, okay. The elastic property of this material is increases means the velocity of the sound will be increases in solids, okay. Here we are going to do one problem, example problem, page number 61 it is given, okay. All of you take your book and listen the problem, and after that you have to copy down in the notebook, okay. At what temperature will the velocity of sound in air be double? The velocity of sound in air at 0 degrees Celsius. What temperature will the velocity of sound in air be double? Okay, when it will become double? The velocity of sound in air at 0 degree Celsius. Okay, the velocity of sound in air at 0 degrees Celsius. 0 degrees Celsius, if you are increasing the temperature, okay, to what temperature? It will be double. The velocity of the sound will be double. Okay. So here let us take, let V1 and V2 be the velocity of the sound at the temperature of T1 and T2 Kelvin. Okay. The standard unit of this temperature is what? Kelvin. Okay. So here the unit of the temperature is Kelvin. let us take V1 and V2 be the velocity of sound at T1 and T2 Kelvin. That means at T1 temperature V1 be the velocity, at T2 temperature V2 be the velocity. Okay. So now take T1, that is 0 degree, at 0 degree Celsius means 273 Kelvin. Okay. So first temperature T1 we are taking 273 Kelvin. Okay. And T2 at second temperature we are going to take, along with that particular temperature you want to add this 273 Kelvin. Okay, then only we can get the next temperature. See here the T1, the velocity is equal to V1. Okay, at the temperature of 273 Kelvin, let us take V1 be the velocity. And what is at T2 temperature, V2 be the velocity. Okay, V2 be the velocity at T2 degree, T2 temperature. That is how we can calculate that temperature at T2 means that particular temperature we are going to calculate the velocity. The velocity will become double, isn't it? That particular temperature we don't know. That is, let us take T degrees Celsius plus 273. Okay. So, the ratio of V2 by V1, the velocity of this velocity at T2 divided by the velocity at T1. Okay, that is V2 by V1 is equal to square root of T2 by T1. Why we are taking the square root of T2 by T1? Yes, we all know that the velocity is directly proportional to square root of the temperature. Already we learned the factors will affect the velocity of the sound. Okay, in that we learned the velocity will be directly proportional to what? Velocity is directly proportional to square root of temperature. Based on this equation, we are going to find the ratio of V2 by V1 is equal to root of T2 by T1. Okay. So, T2 be the temperature, okay, at the velocity of V2. Okay. And when the velocity of V1, T1 be the temperature. Okay. And here it is equal to T2 means what we written already. T2 means 273 plus T degree. Okay. That temperature we don't know. That's why we are taking T degrees Celsius. And T1 here already given 0 degrees Celsius means that is 273 Kelvin. Okay. So we are going to calculate V2 by V1 is equal to 273 plus T divided by 273 is equal to 2. This 2 denotes what? Here is to see the question. The velocity, at what velocity it will become double. At what temperature the velocity of the sound will become double. Double that value they given. No. That's why here we are taking this 2. Okay. V2 by V1 is equal to 2. At what temperature? At what temperature? This T only we are going to calculate. At what temperature the velocity will become double. Okay. So, V2 by V1 will become double. At what temperature? Isn't it? So, V2 by V1 already root of 273 plus T divided by 273 is equal to 2. Okay, that is given data. Okay. So, next if you are taking the square root, what you will do usually? Yes, if you are taking the square root, here 1, 2 we can multiply. Isn't it? 273 plus T divided by 273 is equal to 2 into 2. Okay. Actually, this square root denotes what? Yes, 1 by T, isn't it? 1 by 2. Sorry, 1 by 2 into this 273 plus T divided by 273. So, next step, if you are taking this 2 here, yes, this 1 by 2 if you are taking here, it will become 2, isn't it? So, 273 plus, if you are taking the square root, yes, that 2 here we can multiply. 273 plus T divided by 273 equal to, already 1 2 is here. Along with that, we can multiply 1 2. 2 2s are 4. Okay. So, next step 273 plus T divided by 273 equal to what? 4. Okay. So, 273 plus T is equal to, next step we have to multiply this 273 here. Okay. 4 into 273. Otherwise 273 into 4. So, 273 plus T is equal to 273 into what? 4. If we are multiplying this 273 into 4, what we can get? 1092. Okay. So, here you can multiply and check it. 273 into 4. Okay. 4 3s are 12. 7 4s are 28. plus 1, 29, isn't it? So here 9, remaining 2. 2 4s are 8 plus 2, 10. Okay, so 1092. 1092. If we are multiplying these two factors, we can get 1092. Then this plus 273, if you are taking this side, it will become what? Minus. Okay, this plus 273, if you are taking this side, it will become minus. So 1092 minus 273. So we can calculate what? The temperature. So if you are subtracting this value, we can get 819 degrees Celsius. So at what temperature the velocity will become double? 819 degrees Celsius of temperature. The velocity will become double the velocity of the sound at 0 degree Celsius. Okay. At 0 degree Celsius, the velocity of the sound is how much? 331 meter per second. Okay. This value will become double at what temperature on? 819 degree Celsius. Okay. That is the answer. Okay. Please copy down this in your notebook. Okay. Next we are going to learn reflection of sound. Okay, reflection of sound. You all know that. What do you mean by reflection? Tell me. Already we studied in the light lesson. Reflection means what? Reflection. What do you mean by reflection? Yes, when the light waves, yes, incident on the surface, it will be reflect back in the same medium. Okay, it will be going in the same medium. That is called as the reflection. We already studied. See here, for sound, if you are speaking, see when you are speaking in the empty room, usually in the hall, if it is no objects are there, if you are going to the new house and if you are speaking there, what you will observe there? What you will observe there? Can you tell me what you will observe? Yes, we can hear the reflection of your sound. See, that is the echo sound we can hear. Okay. That is one of the example of this reflection sound. Okay, reflection of sound. When sound waves travels in a given medium and strikes the surface of another medium, and they can be bounced back or reflected back into the first medium. That process is called as what? Reflection. Here this is the definition of the reflection of sound wave. Okay, when sound wave travels in a given medium. Okay, the sound wave will be traveling in one medium. Okay, and strikes the surface of another medium. Maybe it will be traveling in the what medium? Air medium. Okay, and here it is a wall. Okay, so this is what type of medium? Solid medium. Okay, just example, just okay. So it will be traveling in one medium and strikes the surface of the another medium. Okay, this is one wall, and they can be bounced back. Okay, so this is the rigid wall. Okay, wall. So from that solid medium to it will be what? Reflected back. Okay, in the same medium, bounced back in the first medium. First medium means what medium it will be traveling first. Okay, that medium itself it will be what? Reflected back. Okay, so this process is called as what? Reflection. Have you all understand, ma? Yes, when sound wave travels in a given medium and it will be strikes the surface of another medium, okay, and then can be bounced back in the first medium. That is called as what? Reflection. Okay, the same process only it will be takes place in the reflection of light also. The similar process it will be takes place in the reflection of light. See here, when a man is speaking, so the sound wave will be traveling in the air medium. Okay, and there it will be what? Striking the wall. Okay, that is what medium? Solid medium. Okay, so and after that it will be reflected back in the same medium. Okay, that is air medium. That is called as what? Reflection of sound. So next we are going to learn the laws of reflection. Okay, light waves, the sound waves also will satisfy this law. Okay, law of reflection. Here, when the sound wave is travel in the given medium, okay, that is the air medium. This is called as the incident wave or the original wave, okay, and it will be strikes the surface of the another medium, okay, that is called as the barrier, okay, and it will be strikes the surface of this another medium and it will be bounced back in the same medium, okay. So this is the reflected wave, and this perpendicular line drawn that is called as the normal, okay, this line is called as the normal. And here this angle between this normal line and this original wave or the incident wave is called as the angle of incident. And here the angle between this reflected wave and this normal is called as what? Reflection. Okay, so here two laws are there. The first law states that the incident wave and the normal to the reflecting surface and the reflected wave at the point of incident all lie in the same plane. Okay, what is the first law? States that the incident wave, this is the incident wave and this is the normal at the point of incident, this is the normal. Okay, normal to the reflecting surface and this is the reflected wave. Okay, these three waves will lie in the same plane. Okay, this is the first law. These three waves will lie in the same plane. Incident wave, the normal to the reflecting surface and the reflected wave. Okay, at the point of incident, this is the point of incident, all lie in the same plane. The second law states that the angle of incident is equal to angle of reflection. These two angles are equal. Okay, these two angles will be equal. Okay, so here if you are getting 30 degree, okay, here also it will be equal to this 30 degree. Okay, so the angle of incident is equal to angle of reflection. Okay, angle of incident is equal to angle of reflection. Okay, these are the two laws of reflection. Okay, and here what do you mean by incident wave? The sound wave travel towards the reflecting surface is called as the incident wave. Okay, here I written original wave is also called as what? Incident wave. Okay, the sound wave travels towards the reflecting surface. This is the reflecting surface. Sound wave travel towards the reflecting surface is called as what? Incident wave or the original wave. And the sound wave bounces back to the reflecting surface. Sound wave bounces back from the reflecting surface. Sound wave after after strikes the reflecting surface, it will be bounce back to the same medium. Okay, so sound wave bounce back from the reflecting surface is called as what? Reflected wave. Okay, sound wave bouncing back from the reflecting surface is called as what? Reflected wave. And the perpendicular line drawn at the point of incident. Okay, this is the perpendicular line drawn from the point of incident. That line is called as what? Normal. Okay, here angle of incident is noted by I, angle I, angle of reflection is noted by angle R. Okay, so the reflection of sound waves, laws of reflection we already learned. The incident wave, the reflected wave and at the normal to the reflecting surface all lie in the same plane. Angle of incident is equal to angle of reflection. That is the second law. Okay, now we are going to learn the reflection at the boundary of the denser medium. Okay, how the reflection will takes place at the boundary of the denser medium. Okay, so just listen this diagram. So here this is the incident wave. Okay, it will be traveling in the medium. Okay, and it will be what? Touch the boundary of this denser medium. Okay, so here in the longitudinal waves, what will be producing? Compression and rarefaction will be producing. Okay, this is a type of what wave? Longitudinal wave. So the longitudinal wave travels in a medium in the form of compression and rarefaction. Okay, so this area it is called as compression and this is called as what? Rarefaction. Here the compression traveling in air from left to right and reaches the rigid wall. Okay, so that is compression, rarefaction, like that compression, rarefaction. After that the compression traveling in air from left to right and reaches the rigid wall. Okay, and this compression will be reaching the rigid wall. Okay, so next what will happen? It exert a force on the rigid wall. So this compression will exert a force on the wall. Okay, so certain force will be while it is traveling, it will be reaches the rigid wall, it will be exerting certain force on the wall. Now the wall also will exert the opposite force. Okay, the wall exert an equal and opposite reaction force. Okay, so the reaction force R can be, if F be the force, it will be incident on the rigid wall, and the rigid wall also exerting a opposite force, opposite reaction force, that is R is equal to minus F. Okay, so the compression will be exerting a force on the rigid wall, the rigid wall also exerting opposite force on the air. Okay, so the wall exert an equal and opposite reaction force, that is R is equal to minus F on the air. So what is the result? So result, the compression is formed nearer to the rigid wall. Okay. So here next what will be forming in the rigid wall? Because of this exerting the opposite force, again what will be producing? Again this compression will be producing in the rigid wall. Okay. So this area will be more compression because certain force will be incident on the wall. The wall also exerting a opposite reaction force. So okay, again the compression will be formed in the air. Okay. That is, this is the incident wave and this is what wave? This is the reflected wave. What wave? This is the reflected wave. Okay, reflected wave. So the reflected wave, so nearer to the wall, again what is producing? Yes, compression is producing. Okay, again it will be what? This is the reflected wave. Okay, so reflected wave will be traveling from right to left. Okay, this direction. Okay, so now the compression traveling towards the rigid wall is reflected back as again what? Compression, and this direction is reversed. Okay, so the reverse direction, again this reflected wave will be traveling. Okay, so this is the direction of the incident wave and this is the direction of what? Reflected wave. Okay, so these are the points you have to learn under this reflection at the boundary of the denser medium. Okay, first point what we have to write? Yes, longitudinal wave travels in the medium in the form of what? Compression and rarefaction. See, more pressure region is there, that is compression. Less pressure region is, that is what? Rarefaction. Already you know. The second one, the compression traveling in air from left to right. Okay, so this direction left to right it will be traveling and reaches what? Rigid wall, and reaches the rigid wall. And when it is reaches the rigid wall, it exerts certain force. Okay, it exerting certain force. Okay, and the rigid wall. The wall will, also will exert a opposite reaction force. Okay, the wall will exert a opposite reaction force on the air. Okay, so the reaction force, it is equal to minus F. Okay, reaction force is equal to what? Minus F. Okay, and what is the result it will be getting? Means again the compression will be formed nearer to the wall. Okay, so result in the compression is formed nearer to the wall. Again it will be the direction alone, it will be reversed. Okay, so the compression traveling towards the rigid wall is reflected back as again what? Again nearer to the wall, what will be producing? Compression. Okay, but it will be traveling in the opposite direction. The direction is reversed. Okay. So next we are going to learn the reflection at the boundary of a rarer medium. Okay, just now we studied about the reflection at the boundary of a denser medium we studied. Now if it is a rarer medium, means what will happen? Okay, now let us consider the sound waves travels in the form of compression and rarefaction, and this compression will be reaches the what? Rarer medium. Okay, the interface of the rarer medium. Okay, now here what will happen? It is a rarer medium. Okay, so it also will be exerting certain force on the rarer medium. Okay, so this compression exert a force on the rarer medium. What will happen? Yes, rarer medium has smaller resistance for any deformation. Okay, comparing to solid medium, it is less. It will be exerting a less force. Okay, rarer medium has smaller resistance for any deformation. So the surface is pushed backwards. Okay, again, so this it will be, it can able to what? Push backwards. Okay, that's why here nearer to this rarer medium, again what will be forming? Yes, rarefaction is formed. Okay, not compression. So in the previous case, again here what will be forming? We studied is compression. Okay, but here in this reflected waves, here what will be forming? Rarefaction is forming. Because what is the reason here? It is the rarer medium. So here the elastic property, it is less, isn't it? So it will be what? It easily takes place the deformation, isn't it? Rarer medium has smaller resistance for any deformation. So the surface is pushed backwards. Okay. So here the particles of the medium, so in the rarer medium, again nearer to the wall, what will be forming here? Yes, rarefaction is formed. Okay. Now listen here. Consider a wave traveling in a solid medium striking on the interface between the solid and the air. Okay, so this is first it will be traveling in what medium? Solid medium. Okay, and it will be touching the interface of the solid and air medium. Okay, the compression exert a force F on the surface of the rarer medium. Okay, the compression will exert a force on the surface of the What medium? Rarer medium. So rarer medium has smaller resistance for any deformation. So rarer medium means it will exert a less pressure, isn't it? So rarer medium has a smaller resistance for any deformation. So the surface is pushed backwards. Okay, the surface is pushed backwards. So the particles of the medium, that is in the rarer medium, are free to move. Okay, rarer medium, already you know that it is loosely packed. The particles are loosely packed, isn't it? So it can able to move easily. So it can particles of the medium are free to move. So the rarefaction is produced at the interface. Okay, again here what will be producing at the interface? Again this rarefaction will be producing at the interface. So the compression is reflected as a rarefaction and it will be travels from right to left. Okay, so here what will be producing here nearer to the interface? Yes, rarefaction is producing, that is a less pressure region, isn't it? So rarefaction again it will be travels in the air from, so first it will be traveling from left to right, again it will be traveling from right to left. Okay, first left to right, again it will be reflected back and it will be traveling from this direction. Okay, so this is the reflection at the boundary of the what medium? Rarer medium. Next we are going to learn the reflection of sound in different surfaces. Okay, so in this picture the different surfaces are there. Okay, the first one is the reflection of sound in the plane surfaces. Okay, a plane smooth surface. So here when this reflection of sound in the plane surface, it will be travel in the given direction and it will be satisfy the laws of reflection, isn't it? It will be bounce back in the same medium. Okay, so the intensity of this reflected wave will be neither decreased nor increased. Okay, the intensity of this reflected wave it will be same. Okay, so what will be the incident wave? The same, it will be reflected back. Okay, the second one is convex surfaces. See here, when this sound waves, it will be incident on the convex surfaces. What will happen? It will be reflected back in various directions. So here the intensity of this sound reflected wave is changed. Okay, the sound waves are reflected from the curved surfaces. The intensity of this reflected waves will be changed. If it is a convex surfaces means what will happen? It will be diverged out. Okay, the reflected waves from the convex surfaces, it will be diverged out, and the intensity of this sound, what will happen? It will be decreases because it will be spreading in all direction. And the next one, if it is a concave surface means what will happen? If it is a concave surface, the reflected waves are converged. Okay, at the particular point all the rays will be what? Incident on the particular spot, isn't it? That black color spot, it denotes that. Okay, the incident, the parallel rays after reflection, it will be converged in one particular point. So here what will happen? The intensity of the sound wave will be increases more. Okay, and if it is a parabolic surfaces means the reflection of sound, it will be the parabolic surface, many halls are designed with the parabolic reflecting surfaces. Okay, and also the different surfaces, elliptical surfaces are there. If it is an elliptical surface means sound from one focus will always be reflected to other focus. Okay, and what matter? No matter where it will be strikes, in which place it will be strikes in the wall. Okay, so like that the reflection of sound will be takes place in different surfaces. So now we can go through all the points. Now what we learned, reflection of sound in plane and curved surfaces. Okay, so the first one, when the sound waves are reflected from the plane surface, the reflected waves travels in a direction according to the laws of reflection. Okay, just now we studied the laws of reflection, and here the angle of incident will be angle of reflection. That is, the intensity of the reflected wave is neither decreased nor increased. What will happen? The same, what will be the incident wave, the same only it will be reflected back. Okay, so the intensity of this sound wave neither be decreased nor be increased, it will same. Okay, but when the sound waves are reflected from the curved surface like convex and concave and parabolic surfaces, okay, here and all the intensity of the reflected waves will be changed. And if it is convex surfaces means the intensity of this the reflected waves will be diverge out. Okay, so if it is a convex surfaces means it will diverge back in all directions, so the intensity of the sound will be decreased. Okay, and if it's a concave surface means what will happen, all the waves it will be, okay, all the reflected waves it will be what converged in one particular points. Okay, after reflection it will be converged in one particular point. So here the intensity of the sound wave will be increase or decrease? Yes, it will be increases. Okay, and the parabolic surfaces it is used to record to focus the sound at a particular point. Okay, parabolic surface mostly why they are using means it will be one person is speaking at one particular point means it will be focused the sound at the particular point. Okay, so many halls are designed with the parabolic reflecting surfaces. Okay, then elliptical surfaces, the sound from one focus will always be reflected to other focus no matter where it will be strikes the wall. Okay, elliptic surface means always it will be, or the sound it will be reflected to other focus. Okay, one particular place one person is standing and speaking, that's a particular sound it will be what focused to other point also. So this same principle it is used in designing the whispering halls. Okay, here this whispering halls, one person is standing in speaking to one particular focus. It can be heard clearly by the listener standing at the other focus. Okay, so example what we can say means one of the famous whispering gallery that is St. Paul's Cathedral Church. Okay, that is in London. Okay, now we can see the picture of this St. Paul's Cathedral Church in London. This is one of the famous whispering gallery. That name is St. Paul's Cathedral Church in London. Here also we can see the images of the whispering gallery. Okay, that is the shape of this whispering gallery. It is what shape? That is the parabolic surfaces. Okay. Hope you all understand today's topic, isn't it? Okay, now I am going to give some homework. Okay, you have to be learn and write in your notes. First question, velocity of sound waves. Two types of velocity, particle velocity. You mark it, particle velocity and wave velocity. Okay, so the wave velocity, this formula velocity is equal to distance by time, and distance traveled by one wavelength lambda and time period t. So this formula v is equal to lambda by t, and here the frequency n is equal to 1 by t. So we are substituting in the above equation v is equal to n lambda. Okay, and the velocity of sound is maximum in solid because they are more elastic in nature than liquids and gases. Okay, and gases are least elastic in nature. The velocity of sound is least in gases medium. Okay, so up to this one important for one word question. Okay, velocity of sound is greater in solid than liquid and gases. Okay, this one question you have to learn and write. Then what are the factors will affect the velocity of sound in gas? Okay, in gas what are the factors will affect? Okay, in gas what are the factors will affect the velocity of sound? That is the effect of density, fully effect of temperature, this equation, and below that you have to mention what is V0 and effect of relative humidity. Up to that you have to learn and write. Okay. Then one more question, what is reflection of sound? Definition, when sound waves travels in given medium and strikes the surface of another medium, they can bounce back into the first medium. This phenomena is known as reflection. Okay, and the same page number 62, here the loss of reflection is there. Okay, there are loss of reflection. What is the loss of reflection? The 2 points just you have to learn. Okay, these 2 points you have to learn. Next question, reflection at the boundary of a denser medium. Okay, so from here to here. Okay, point wise you have to mark it and learn, and this diagram also, the reflection at the boundary of the denser medium. Okay, page number 63. Same page number, reflection at the boundary of rarer medium. Okay, this is one of the book back question. Okay, this two boundary of this rarer medium also. Up to here you have to learn. This diagram also you have to mark it. Okay, and the reflection of sound in the plane and curved surfaces. Okay, Here also when I am teaching, I given all these points point wise. So just you have to note it point wise, and you have to learn the reflection of the sound wave in the different surfaces, plane and curved surfaces. Okay, so learn all these questions and you have to write one by one. Okay, we are getting weekly only, one period only, so you have to be, don't waste your time. You have to sit and learn and write it in your notebook. Okay ma. Then one more thing I have to give, we are going to do the practicals. Okay, see, you have to take page number 335. Okay, page number 335. In that, the first practical they given. Okay, so you have to take one note. Okay, long size note. If it is 100-page note also, no problem. Okay, so you have to take that note and you have to write that first practical observation, determination of weight of an object using the principle of moments. Okay, first you have to write this aim, apparatus record. Okay, everything in the right side of this page you have to write it in the right side. Okay, left page you have to leave for drawing and observation. Okay, the tabular column. Okay, so right side you have to write it. Okay, to determine the weight of an aim you have to write it, apparatus you have to write it. Here the formula is not given, so you have to next you have to third point you have to write the formula. Okay, formula here not given. Okay, but the same page number, here it is the formula, unknown weight W1 is equal to W2 into D2 by D1. Okay, and here W1 denotes the unknown weight, W2 denotes known weight, D1 distance of unknown weight, and D2 distance of known weight. This 4 also below the formula you have to write. Okay, after writing this formula you have to write the procedure. Okay, procedure. Okay, so everything it is in the what page? Right side of this notebook. Okay, then left side, first when you are starting page you have to draw this diagram. Okay, in the left page first you have to draw the diagram. Okay, and the next page left side you have to draw the tabular column. Okay, you have to draw the tabular column, use pencil and draw okay, tabular column, and the diagram also you have to use pencil. Okay, and the after doing everything you can write the result. Okay, result right side only, after the procedure only you have to write this result. Okay ma. So this also you have to be start writing in the observation note. Okay, take one long size note. Okay, 100-page or 200-page, no problem. You have to take it and start to write the first practical. Okay, have any doubt you have to ask in the interactive class. Okay, thank you students.